Hello, everyone. Welcome to another webinar of the Quantum Fluids Network. Today's speaker is Professor Kamran Behnia from ESPCI in Paris. He's going to talk about heat propagating in normal liquid helium-3. So whenever you're ready.
Thank you.
Yes.
Okay. I would like to thank you for giving me this opportunity to present this work. Let me begin by mentioning that the work I'm going to present, this was published last year. My co-author, Kostya Trachenko, based in London in University Queen Mary, tragically passed away a few months ago, actually, just 1 year after the publication of this paper. And really, I met Kostya only 3 times during my whole life. Actually, we met and we are talking about subject. None of us is an expert of liquid helium-3. I am a metal physicist interested in thermal transport, and Kostya was interested a lot about how you can explain condensed matter physics, and in particular liquids, just by looking at fundamental constants. And when we met in Spain just at the beginning of the pandemic crisis, we had an exchange, and we found that we have something to share and we have to discuss. And as you are going to see, what I'm going to present is a hand-waving solution to a very old program. This is not a rigorous calculation, but yet I think it is rather convincing. And I hope you are going to see what's going on. Please interrupt me whenever you have a question. Okay, so what I'm going to talk about is the theory of Fermi liquid. Okay, so I am interested because I have been measuring thermal transport in metals, superconductors, semiconductors, whatever, for like 30 years. And we believe that everything is understood. You see, the starting point is this paper of 1959, where Abrikosov and Khalatnikov derived the properties of liquid helium-3 at low temperature. This theory became extremely prestigious when strongly correlated metals were discovered many decades after these heavy fermion systems in which the theory seemed to work. So what are the transport properties predicted by this theory? It is that viscosity is going to be proportional to the square of the inverse of temperature, and thermal conductivity would be proportional to the inverse of temperature. And these are the formulas from this article of 1959. So you have very complicated prefactors. Actually, they are very important for our discussion at some point, but I'm going just to be interested in the temperature dependence. So you see, normally thermal conductivity is 1/T and viscosity is 1/T squared. Now, viscosity for electrons in metals, you cannot measure it, but you can measure thermal conductivity, and of course, compared to electrical conductivity in metals. And you see, there is a law, very old law of condensed matter physics, which is the law of Bridgman and Franz, discovered in 1853, where if you measure thermal conductivity of a metal and divide it by temperature and divided by electric conductivity, then you have what is called the Lorentz number. And this Lorentz number at 0 temperature is going to become equal to a ratio of fundamental constants. So if you look at entropy conductivity, which is thermal conductivity divided by temperature, and compared with electrical conductivity, you can also talk about entropy resistivity, which would be the inverse of this guy in the same way that you have electric resistivity. Okay, now, if I go to the metal physics language, the thermal conductivity of helium-3, which is 1/T, as the Fermi liquid theory is predicting, is equivalent to say that the thermal resistivity, entropy resistivity, if you wish, if we want to compare with electrical conductivity of metals, is T squared. And this is what you can do. If you plot this quantity, you see that at low temperatures, it is indeed perpendicular to T squared. This is actually the data by several groups. I am going to focus mostly on data by Gray-Wall, which is the most extensive set of data at low temperature. But actually, this property was measured by many groups in 1970s. So the thing is that in metal physics, and this is how I became interested in this subject, we have something called the Kadowaki-Woods ratio. If you look at different metals, different electronic Fermi liquids, you see that correlation can go from weak to strong. So if you measure your A, the prefactor of this T square electric resistivity, then you see that it is going to scale with the square of electronic specific heat, which is basically normal because both of them are proportional to the density of states. And what we did in 2018, when we were looking at this thing, that actually you can put helium-3 here. So the red points are the thermal resistivity data points. Thermal conductivity is harder to measure. So you see that these data points are much fewer than the black data points, which are about electrical resistivity. But you see that there is a continuity. So the whole idea is that in metals, you have also a T-square resistivity, and the larger the collision cross-section of electrons, the larger would be this number. And this scales with the density of states. So there is a continuity, but since 2018, when I become interested in this material, actually, I found that the case of helium-3 is not as well understood as we believed. So this is the outline of my talk. The first thing is just advertising the fact that this T-square regime in helium-3 is extremely narrow, contrary to what was previously believed. That the second is that, well, this is actually not something which means that the Fermi liquid theory doesn't work. It means that the Fermi liquid theory is not restricted to the picture of a gas of quasi-particles. There is a collective mode, a sound mode, which is carrying heat. And I'm going to use, again, very simple arguments to derive this. The first is to use a quantum version of the Bridgman formula for liquids. The second is to do it from the other point of view, begins with Landau conduction as transmission, and show that if we look at entropy transmission, we find the same formula, the result is the same, and this matches very well the experiment. After this, I come back to metals, and I would like to discuss in a few minutes about the consequences of this picture for metallic Fermi liquids, and this may provide possible solutions to two distinct mysteries. Okay, the starting point. You see, in 2016, the editors of Report on Progress in Physics asked Tony Leggett to write a review paper on liquid helium-3 because it is believed to be the best understood Fermi liquid. Now, what is interesting is that Leggett in this paper begins his paper with a disclaimer, which is stated here. One thing should be emphasized at the start. When we say that we have a semi-quantitative understanding of the properties of liquid helium-3, this claim is really justified only over a rather small region of the parameter space. This is true. Now, how small is this parameter space? You see, you should be at a temperature much smaller than the Fermi temperature, the wave vector much smaller than the Fermi wave vector, and at frequencies much smaller than the Fermi energy divided by h bar. So he stated that in practice, actually, you need to go to 100 millikelvin. Given that the degeneracy temperature, the Fermi temperature, is something between 2.7 to 5, according to what effective mass you put, this is very small. This is of the order of a few percent. But as you are going to see in a minute, actually, this is an understatement. So here is the most extensive set of data by Gray-Wall measured in 1984. Again, this is not the only set of data. This is the most complete. Basically, people agree within a few percent on the quantitative numbers. So as you can see here, you see the region in which we have this 1/T thermal conductivity is very narrow. So these curves A, B, C, D, E are at different pressures, so at different molar densities. So A is at ambient pressure, where you see that this T-linear regime maybe extends up to 20, 30 milli-K, but not at. When you go to E, where you are close to solidification, actually you almost never attain this regime of 1/T. There's always a deviation. And what is surprising is that clearly all curves converge towards a regime where conductivity, thermal conductivity is increasing following a square root of T behavior. This occurs at a temperature of the order of a fraction of the Fermi temperature, maybe 0.2 TF. And as far as I know, nobody has treated this problem. Even if Greywall, as you can see in this figure, stated this without any extensive comment about the origin. Okay, so the first question is, what's going on? Very well, at very low temperature, this 1/T behavior holds, but why there is a deviation and why does it become an increasing function of temperature following the square root of T? Okay, actually the answer is simple in the sense that if you're familiar with classical liquids, you know that in classical liquids, you do have phonons. For me, it was news. You see, when I met Kostya in 2020, phonons in liquid, how come? But of course, there is one. You can begin by considering the fact that you see the pair correlation factor is oscillatory. So this is a figure from Wikipedia, if you wish. This is pair correlation function for the 3 states of matter. This is simulations for argon. So you see, if you have a gas, you have a pair correlation function which decreases continuously with no oscillations. Of course, in a solid, we have a periodic oscillation, but in a liquid, we continue to have this oscillation. It means that the presence of an atom somewhere favors the presence of other atoms at regular intervals. This is something that, of course, we know. And experimentally, people have seen phonon dispersion using neutron scattering. So, you know, again, this is not a discovery. This is something which is not well known. So you see, you can talk about rotons if you wish. You have a minimum in phonon dispersion of liquids. Since then I have discussed with many theorists, and there is a general consensus that this word roton is unfortunate because it makes helium, superfluid helium exceptional, where there is nothing exceptional about having this minimum here. So this is not the whole story. The story is that actually, if you are interested in thermal transport in a classical liquid, phonons play a central role. Actually, there is a formula for this thermal conductivity, which was given by Bridgman back in 1923. It's very simple, and it's very successful. The idea is that basically, if you want to know what is the thermal conductivity of water or ethanol or whatever, what you only need to know is the sound velocity and the density. Here you have the Boltzmann constant, and basically there is a prefactor which is between 2 and 3. So you can change it, and this formula is, of course, very hand-wavy. It works very well. You can see where does it come from. Basically, it is the product of an entropy density. A equipartition will tell you that it is of the order of KB, the sound velocity, and the mean free path. So the fact that you have a sound velocity here implies that heat is not carried by individual molecules, the particles of the liquid, but it is a collective phenomenon. And here is experimental data in the most common liquid on this planet. So the three phases of H2O, and the Bridgman formula expects that the temperature variation is small because the only thing which can vary here significantly is sound velocity, which does not change much from 0 to 100 degrees Celsius. Okay, and this formula is not even used. People propose ameliorations to explain, for example, the thermal conductivity of various quantum liquids. And as you can see, the agreement with experiment is not that bad. Okay, maybe before going further, coming back to helium-3, I should say something about how this can be understood. These, the curves I just showed. For that, I need to switch to thermal diffusivity. So the heat equation is about the temporal variation of temperature. As you can see, you have a diffusion. This is, and you have a thermal diffusivity, which is expressed in meters squares per second. What we measure in a steady state experiment is the thermal conductivity defined by Fourier's equation, where you have the heat flux proportional to your temperature gradient. So kappa is thermal conductivity and D is the thermal diffusivity. And these two quantities are related by a specific heat per volume. Okay, so if I have the thermal conductivity, you just need to divide it by the thermal diffusivity, which can be measured independently by a time-dependent experiment, and then look at thermal diffusivity. And note, this is the same data shown for thermal diffusivity. So after the division by specific heat. Again, you see the three phases, but now I can explain easily to you how do we understand these three phases and their transport. What is interesting is that in the solid state, ice, you see a thermal diffusivity, which is basically of the order of the square of sound velocity divided by this time, the so-called Planckian time. So I'm not going to talk about this. Actually, it is surprising to see that even in ice, you can see quantum mechanics in this slope of your thermal diffusivity. In the liquid, in water, you see that thermal diffusivity is much smaller and it is almost constant. And you can see that it is not very far from the product of 1/3 of the product of the sound velocity and the intermolecular distance. Basically, this is the Bridgman formula. So the heart of Bridgman formula is that it is nothing else that the Motyoffe-Regel limit for phonons. If phonons can only go as far as the distance between atoms, you get this diffusivity. And basically, if you multiply it by a specific heat, then you get the Bridgman formula. And finally, in the vapor phase, you have this square root of T diffusivity, because now the velocity is no more the sound velocity. The relevant velocity is the thermal velocity of individual molecules. Okay, so you see, this is a simple picture, but you don't find it in textbooks for some unknown reason. If now we come to our case, before going further, let's go to a place where you can get rid of this phase transition. Okay, if you go above the critical point, then between the liquid and the gas, there is no thermodynamic phase transition. But as you can see here, again, this is the data for water. You see that the system keeps the memory of this minimum. The thermal diffusivity goes to a minimum. And this is something actually that Costia observed in many, many liquids. All of the cases in which there is a documentation, we see that both viscosity, which is the diffusion constant for energy, for momentum, sorry, and thermal diffusivity, which is the diffusion constant for thermal energy, both of them in all documented fluids show this kind of minimum. And the reason is that you cannot go below an unbreakable bottom which is set by the velocity of your collective mode, the sound velocity, and the interdistance and the distance between particles. If these two quantities are bound, which is the case in any condensed matter, the distance between particles and the velocity, then you will have a minimum diffusion constant for these two quantities. And this is how the system cannot avoid this minimum. Okay. After this, I can come back to the case of helium-3. So what I'm plotting here is thermal diffusivity data, again by ÇHE. Actually, in his paper, he has plotted this curve, well, the inverse of the thermal diffusivity, without discussing. So you see, thermal diffusivity, both at zero pressure and at 3 megapascal, just before solidification, has a minimum. And the question is, where does it come from? So now that we understand what's happening in classical liquids, let's come to this quantum liquid and try to see why a minimum also occurs here. So the reason I am showing this figure is that helium-4 and hydrogen are liquids which have particles with the closest mass to helium-3. Are of almost the same order of magnitude. So the diffusion constant, the physics should be similar. And actually, the vertical axis is common between these two plots. But here, we are at 3 megapascal. And in 3 megapascal, both these liquids are classical, are no more quantum. Please see that the horizontal scale is very different. We are at high temperature for these guys. And why do we see minimums here? Well, the explanation is what I gave discussing the previous slide. At high temperature, heat propagates thanks to particles. So as you cool down the system, you are going to decrease the thermal velocity of your particles. You are going to decrease their mean free path. So diffusivity goes down. But at some point, you cannot go further down. Why? Because you have a collective mode set by the lowest minimum, mean free path, which is the interparticle distance, and the velocity, which is the sound velocity. Here is how you get these two minimums here. Okay, how about the quantum liquid? Here, you begin by the cold side. You have a gas of quasi-particles, where you begin to have collisions with them. Now, with warming, the mean free path is going to go down. So, if it continues, at some point, this thermal diffusivity is going to become zero or very small. And it cannot be for the same reason here, because here you are going to have some kind of collective mode. In the case of classical fluids, this is just ordinary phonons. In the case of the quantum fluid, the most plausible explanation is that you have also sound mode because you have a collective mode. We know that there are collective modes there. The question is, why is it there and how can this operate here? So if I now reformulate the problem is that, okay, when there is no quantum liquid, the situation is like that. In a solid, of course, heat is carried by phonons, itinerant phonons. In a classical liquid, you have still phonons, but these are localized phonons. This is why the Bridgman formula works. And only when you are in a gas, heat is carried by particles. Now, if you have a quantum liquid like helium-3, at the beginning, at very low temperatures, you have actually gas of quasi-particles. When the liquid becomes classical above its degeneracy temperature, you can use the Bridgman formula. Again, it doesn't differ from a classical liquid. And now the question is, how can you go from this situation to this situation? Most probably, you need a version of phonons which are not itinerant like a classical liquid, mobile. So there are phonons which are not like a classical liquid. But what would be this situation? Okay, so this is an interesting problem, and it has never been solved because actually this is a table of what we know about heat propagation by sound in different kind of condensed matter. You know, in crystals, if you have very low temperature, you expect phonons to vary, to have a thermal conductivity varying as cube of temperature. If you go to very high temperature, then you expect to have a 1/T behavior for phonons. If you look at glasses, thermal conductivity is, instead of being cubic in temperature, it is quadratic in temperature. If you go to high temperature in glasses, like in liquids, in both cases, you have a flat thermal conductivity. So none of these matches a thermal conductivity which varies as a square root of T. So this is an unsolved problem. Okay, I'm going to try to give you a solution, and we are going to compare it with the experimental data by Gravel and others. But before that, you know, actually to do that, I will do it in two different ways. Both of them are not very rigorous, but I hope they are convincing. The first is trying to make a quantum version of the Bridgman formula. So you see, in graduate school, we learned that the way to make a classical formula quantum is to look for a crossover between the classical limit and the quantum limit. It is often about the distance between particles and their thermal wavelengths. So if we do the same thing for this formula, you are going to change the three things. The entropy density, which was just of the order of the number of particles, you had an equipartition, you should imagine that it becomes like a specific heat, kBT by TF. We have fermions. The velocity, you can replace sound velocity by Fermi velocity, and the distance between particles, which is here in the shape of this n to the power of 2/3, should become replaced by the thermal wavelengths of your particles. If you do this, okay, at the end, it is surprising because h bar disappears. You have both in numerator and denominator h bar. So you will end up by having a formula which keeps n to the power of 2/3 like Bridgman's formula. The prefactor is different. You have kb, and it is a square root of t. Okay, of course you can say, well, this is not serious. Let's try another way of having the same expression. So you may be familiar with Landau's picture of conduction as transmission. So it began as a reflection on how charge travels in a 1D vial, but it became very successful. So Landau-Buticker's formalism is now used to understand quantum Hall effect and many other phenomena where you cannot avoid, the quantum mechanics. And you see, one way of understanding the root formula in this picture is to say that if you have a spherical Fermi surface, you can count the number of the modes. So 1/3 comes from the dimension 3, 2 comes from the spin, and then you have this kind of counting the number of channels. And if you do this, you can see that your root formula is nothing else than this formula, where you can have a conductivity expressed as the product of the quantum of conductance, this prefactor times kF squared, and the mean free path of quasi-particles. These two expressions are identical. But contrary to the root formula for conductivity, here you see immediately that you have a quantum of conductance, E squared divided by h, times the number of channels and the mean free path. And of course, you can use the Widman-Franz law and do the same thing for thermal conductivity. And if you do that, you find that the same root formula for thermal transport gives you, the prefactor is different, but again, you have the quantum of thermal conductance, kb squared divided by h, times the kf to the power of 2 times the mean free path of quasi-particles. Okay, imagine now that in addition to this quasi-particle transport, we have the whole Fermi surface moving with the same number of channels with a single mean free path, which we assume to be the Dobroi thermal length. So the Dobroi thermal length, if you want a physical intuitive picture of it, is actually what determines the sharpness of your Fermi surface in reciprocal space. It is a measure of the thermal smearing of your Fermi surface at finite temperature. So if you put this, actually, you see that you find exactly the same expression that we found coming from the Bridgman formula towards quantum mechanics with the same prefactors, which may not be surprising because we are just making a kind of census of the number of states available. Okay, let's compare this to the experimental data. So here what I'm showing is Gray-Wall's data, but I'm plotting the entropy conductivity, thermal conductivity divided by temperature. This is why there is no minimum. It begins as T-2 in very low temperature, and then it becomes softer and softer. And in addition to Gray-Wall's data of 1984, there is a data set by Murphy and Meyer 10 years afterward. They didn't measure under pressure. They didn't use, so their measurements was not adiabatic, but isothermal. So there is some, but you see that the mismatch is not that great. Now, if I put the expression I just said, this is what I get. So the blue line is basically this expression, this simple-minded expression with no adjustable parameter besides the density, which we know, and the effective mass, which also we know from a specific heat. So you see that, well, the agreement is of the order of, the discrepancy, if you wish, is of the order of 10%. And after we found this, we were surprised. How come that this very simple-minded experiment can give you an expression which suggests that actually you expect to have a square root of T dependence with the right prefactor? We asked ourselves, maybe we can explain the whole temperature dependence just by a fit, where you have a quasi-particle channel, which goes like T-2, and then a additional channel, which goes like T-1/2. And here, we succeeded in, as you can see, in these two fits, the data set is the same. These are the same plots. I am putting it in kappa not for cheating, just to say that actually the agreement is not perfect. You have some difference. A referee of our paper asked us, have you assumed any coupling between these two modes? Of course, we did not. And of course, you can improve the model and the agreement by assuming that if you have two channels, there could be a mixture, a coupling between these two channels, which would lead to a third term. But you see, even at this stage, the agreement between the data and this simple-minded expression is within 20%. This agreement is less than 20%. Okay, so here is the picture. It looks like we have two channels of conduction. The first one is what was known for 40 years, since Abrikosov and Khalaknikov. The whole point is that you have quasi-particles. These quasi-particles bump to each other. The phase space of this scattering goes like the square of temperature, and basically this works. The second channel, which we call sound, this is about the whole Fermi surface moving. This is in real space. You can see it as a heat propagation by sound mode with the shortest possible wavelengths. What is the shortest possible wavelengths? Of course, it is of the order of the interparticle distance. Of course, you can have virtual, waves with these wavelengths here. It doesn't cost you anything because since there is no continuum medio here, these are completely virtual. So if you don't have any temperature gradient, there is no difference between these two waves which have opposite phases. But as soon as you put a temperature gradient, you are going to break actually this degeneracy. So if the cost of having such a wave is affordable energetically, then you have a kind of wave, 2kF, wave vector wave, which is going to carry heat easily. Another way of looking at the same problem is that in solids, we know that we have an acoustic mode at zero, at Q equals 0. Because of the Fourier transform, the same zero mode should exist when you go at 2 pi over A. Everything repeats every 2 pi over A. Now, if in a quantum liquid, we have also a soft mode here, and the reason we can have this soft mode is that the difference between 2kF and 2 pi over A in an isotropic medium like helium-3 is less than 1%, then this is a soft phonon mode being with a mean free pass, which is of this order of magnitude, with this group velocity, and actually the lifetime, which is of the order of the Planckian time. Okay, is there any evidence for existence of such a mode? Yes, actually, the zero sum, which was explored in this experiment, has a soft mode, has a soft, belly here, if you wish. If you look at this, you have an acoustic mode with a dispersion, but it continues to exist here. And then when these guys published this data, there was a comment asking them, actually, can you really believe that you have a mode here? Because the attenuation and the frequency are almost the same. And they answered, yes, they can still, actually, if you look at their data, you can see that near 2kF, which is here, there is a mode, there is a peak. So the state exists, but it is so overdamped that the width is of the order of the frequency. So, okay, after the paper was published, I was informed by my colleague, Henri Godefroy in Grenoble, that we didn't know that because, we have not read this paper, that actually they have already seen this and discussed this in 2D helium-3. So fundamentally, this is not different from 3D helium-3. So actually, we didn't know that the existence of such a collective mode with a 2kF anomaly was already discussed and proposed to the community. What was not mentioned, or what is new, is that this mode seems to be what carries heat in a static, steady state, simple thermal conductivity experiment. It's not only about experiment. People who do Monte Carlo, you see, so I am giving you two different groups. They find actually this Roton mode with a 2kF anomaly. The question is, is it something which goes to zero at zero temperature? So you see that it seems to have a temperature dependence. So at least theoretically, its softness is shown by these simulations. But again, all of this doesn't replace a rigorous theory. Okay, I finished the first part of my talk. I told you that I am not actually doing any experiment on helium-3. What I have been interested in was, metallic Fermi liquids, thermal and electric transport there. But I believe that this way of looking at the best understood Fermi liquid can offer possible solutions to two mysteries. It will not solve the mystery of strange metallicity, systems which seem not to be Fermi liquid at all. But even in Fermi liquids, there are mysteries which we do not understand. The first mystery, which you can guess, is that the T-square regime there is also very much restricted. And maybe this is the possible solution to that mystery. The second is that T-square resistivity in metallic Fermi liquids is extremely robust. And both of these questions are questions for which we had no good answer up to now. Okay, let me begin by the first one. So what you are seeing here is the data on UPT3. So many people have studied this. I did my PhD back in 1980s in Grenoble on this system. So you see, this system has a T-square thermal, electric resistivity. So this is rho. Sorry, I didn't put this is rho in micron centimeter. So you see the range of T-square resistivity is very low. What's happening here? You have a downward deviation. The downward deviation means you have more conduction and not more scattering. This one is lanthanum, strontium, copper, oxygen. Again, this is resistivity in micron centimeter. The range of temperature is very different, but again, you have a downward deviation. Now, if we come to this idea that maybe this physics is also valid there, then instead of fitting your data to rho 0 plus AT squared, you should fit your data to something like that. You have a channel of quasi-particle transport and a channel of sound transport. And as you can see, actually, you can see that the UPT data, this was the same data. Now you can fit it easily. Of course, a fit doesn't prove anything. You know, it's just a heuristic solution. But as far as I know, in any strongly correlated fermionic system that I know, you see, you have this phenomenology and this possible solution. So maybe the most serious case is a strontium ruthenate. Strontium ruthenate is a well-studied Fermi liquid. And again, you have the same situation. T-square resistivity works up to some temperature, well below the degeneracy temperature of your Fermi system, which is of the order of 1,000 Kelvin. As you can see here, the three bands are the three sheets of the Fermi surface have been established theoretically and experimentally. So the question is why this T-square resistivity stops at a few percent of this 1,000 Kelvin? And why then you can fit everything with this second channel conductivity? So again, this would be a possible solution to this mystery. Is there soft-mole metals at 2 kF? Actually, a lot of our theorist friends have worked on strongly correlated metals with a very large RS, and they see that there should be something around 2 kF. So actually, this group is the same group who worked also on helium-3. So again, they find something around 2 kF. So there could be a collective mode in metals. Again, the question is how to provide the rigorous theory of transport by this mode. Please pay attention that now I'm talking about electric transport, not only thermal transport, which implies the possibility that charge neutrality is not preserved by this collective mode. Okay, let me come to the second mystery. The second mystery is that, okay, if you are talking about thermal transport, there is no problem in driving the road, a T-squared thermal diffusivity from the size of the phase space. But when you are talking about electric transport and momentum travel, you need to find a way that electron-electron collisions lead to a loss of momentum current. So the two known roads to this is the one proposed by Bobber, where you have two reservoirs of electrons, one more localized, another more mobile. One of them is stronger linked to the thermal bath. The other is the umklapp. You know, when you have umklapp processes, you can have a loss of momentum because the resulting wave functions minus the initial wave vectors, the resulting wave vectors minus the initial wave vectors is equal to the size of a reciprocal lattice. And this creates a route to leak momentum to the outside void. Now, since 2015, we know that this doesn't work. We have seen it in a strontium titanate. This, I'm not going to inside. This is a system in which You can tune the size of the Fermi surface over 2-3 orders of magnitude, and the T-square resistivity is robust. So people since then have tried to find a solution. So it looks like we don't understand the origin of T-square resistivity in metals because it doesn't need umklapp. And of course, if we have a collective mode, everything will change. Okay, this brings me to the summary of my talk. The first point, the take-home message is contrary to what many people believe. I don't know how well known is this fact. The quasi-particle transport regime in helium-3 stops at a small, very small fraction of the Fermi temperature. It is very easy to explain with hands why above this temperature, the dominant mode is a sound mode with a T-square thermal conductivity. It is possible that such a mode plays a role in transport, thermal and electric in metals. And in that case, a number of mysteries would find solutions. I would just finish my talk with questions for the future experimental research. You know, again, since I'm addressing the quantum fluid community, I would like that, for example, despite the fact that almost everything has been measured in helium liquids, helium-3 and helium-4, we don't still have the data in a wide temperature range for the whole under pressure to see how these two components evolve up to the solidification. Maybe more related to hot topics of today, nobody has looked for a thermal Hall signal in liquid helium-3. You know, these days, there is a lot of activity around thermal Hall effect by phonons in ordinary insulators. So again, helium-3 is a system which is, of course, answers to magnetism, and it would be good that one day somebody measures the thermal Hall effect in helium-3. So with this, I would like to end my talk, and I would be happy to take questions.
Yeah, thanks a lot, Kamran. It was a very illuminating talk. So you're open for questions. Maybe raise your hand if you have a question. Or just unmute your microphone and ask the question. Yeah, waiting.
Hello.
Hello, yeah, we can hear you.
Yeah, okay, thank you. Thanks for the presentation. I think it's very interesting. I have a question about the first part. So if I understand correctly, you think that this the collective mode is this highly damped zero sound in the high temperature regime that also observed by other experiments like X-ray scattering. Is that the interpretation of the formula you proposed?
Yes, it is a very hand-waving interpretations. You see, we are thinking about what is happening here. It is a collective mode, so it's a phono. It has a very short wavelength. So this is why we go to what happens near 2kF. And when we see this anomaly, we see that this is actually where the zero sound becomes ordinary sound. You see, so it is hydrodynamic. If you wish, this is the region where you are hydrodynamic because the particle scattering time, okay, is comparable or shorter than the time between two wave maximum. So, you know, this is the region we make the connection, but there is no direct evidence that what people see by X-ray diffraction is what we see in a thermal conductivity experiment.
Okay. Do you also consider the spin fluctuations? I think people believe that in helium-3 it's an also important collective mode.
Yes, so I am aware of the fact that people were fighting for a long time. It is helium-3, is it a nearly magnetic system
Yes.
or a nearly localized system? I didn't talk about spin, not because it is irrelevant, because we don't need it for our explanation. Our explanation is really about the crossover between a classical liquid in which there is no spin and a quantum liquid. But of course, I cannot rule out the fact that spins play a role.
Okay, thank you. Very interesting. Thanks.
Yeah, thank you. So I think it's Mark now. Mark.
Yeah, thanks. Thanks very much for a very interesting and enlightening talk. And I have maybe a two-part question about the temperature behavior and of the thermal conductivity in helium-3. And so the grey wall data, as you noted, goes up to 1 Kelvin, and there is sort of remarkable that actually all the lines come together at a single point, which you didn't have to do, and that's something that he remarks on. So then, what would you say happens between 1 Kelvin and at higher temperatures up to 3 Kelvin, where it stops being liquid? What would you predict for that?
So actually, I am not a theorist, so I am not predicting something, but you are completely right. So I can tell you how I understand it in that way. So you see, as you know, as you put pressure on helium-3, you increase interactions. So the quasi-particle part changes a lot. All Landau parameters are changing drastically up to the solidification. On the other hand, this collective mode, as far as we see, it should also change some, but not as much as the quasi-particle part. So the reason at high temperature the curves are merging, the way I understand it is that the pressure-induced change in Landau parameters is much more important at low temperature than at high temperature. But again, as I said at the end, we don't have good data between 1K and 3K, where you can really check this.
Yeah, I'd like to see it too. And yeah, just a sort of second part of the question. So your formula, your very nice formula for it, had this sort of prefactor outside of about 2. It was a 1.88 or something like that.
Yeah.
So where does that come from?
It's just a combination. You see, when you do is pi, I don't know on top of my head. You have pi to the power of 7.2, and then at the end becomes 1.88. It's something like that. And okay. What is remarkable, as I said, you get it in 2 ways. And this is where you see, you have a pi 2/3 in a Sondimer expansion thing, which is very important for thermal transport experiments. Then you have other things when you go from cube and thing, and it gives you 1.88.
Okay, right. Thank you very much.
You are welcome.
Yeah, thanks, Mark. So, Andre?
Okay, maybe I put my video on. I don't know if you can hear me. Can you hear?
We can hear you. Yeah.
Okay. My comment is that, okay, it's very nice that one tries to put together the theory and of the explanation of what happens in Fermi fluids from the quantum regime to the classical regime. And this is a rather complex action to undertake. But it turns out that we have a very detailed knowledge of the excitations of these quantum fluids, as well as helium-4 and neon. And okay, so something was shown for neon, and also some X-ray data. In fact, there is an extensive literature on neutron scattering and on helium-3. And the picture we have is very clear. I mean, there is, at very low temperatures, we have this Landau Fermi liquid regime with the lifetime is long, and we have these particle Hall excitations. When we go to higher energies, and these particle Hall excitations, they give rise to collective excitations of the Fermi sphere, and there are 2 kinds of oscillations. And these oscillations are well known. There are zero sound and there are what they are called paramagnons, magnetic excitations. It turns out that the phonon part, the zero sound, is not heavily damped, but it's at higher energy than the paramagnons. And this is contrary to what is observed in high TC superconductors, where the magnetic mode is above the zero sound mode. So my point is that in the regime that we are discussing here, all these excitations are inside what is called the particle Hall band, and all the collective modes are extremely strongly damped. You see? So imagine you come from low temperatures where you have zero sound, but the paramagnons are already damped. They are inside the particle Hall band. And then you go to a regime where everything is a kind of soup, where the energy is broadening, is so big that you can barely talk about collective modes. They cannot propagate very far. And if you have a roton, the group velocity is zero because the omega decay is zero. So it doesn't propagate very far. And then you enter a regime of almost free particles. And this is where you start reaching the classical regime. So my point is, to summarize, is that we know very well the excitations of that. And we have a very good idea of that also through the theory of Eckhart-Kroczek, where the dynamics is calculated with a very good agreement with our experiments. So we know the excitations, we know what should convey heat in these systems. So I think that one should go really in more detail comparing the neutron scattering and the theory, microscopic theories, and that, there are everywhere factors of 2 and 3, and everything is of the same order. All velocities are of the same order. All energies are of the order of Kelvin. The rotons, they are there, but they are just a kind of an effect of correlations that was shown. And I will end up by saying that also the effective mass is not 2.7 or 3. When you are at higher energies, the effective mass is essentially the bare mass of the helium-3 atoms. So when one goes at high temperatures, you are not having heavy fermions there. You're having the standard helium-3 fermions. So you see, I have many, many comments on that. And I think that we should discuss that in more detail.
So, Henri, I have just a very short comment on your comment. You see, I think all what you said is correct, but here are several just facts. The temperature dependence is extremely simple, and it was mentioned by Grable. It is the square root of T. I completely agree that actually the mass evolves from 2.7 to, so, the expression, part of the discrepancy can come from the fact that the mass is evolving. But I am saying you that if you know the Bridgman formula, if you are not contaminated by some stuff, 1923, it was even 30 years before Landau theory. It is again another case of collective amnesia in our community. It's just condensed matter. It's not the first time I'm seeing this. Something was mentioned. The question was forgotten. As far as I know, there is no theory of thermal transport. So I'm not talking about excitations. And the experimental observation is so, simple that at least the order of magnitude in a Fermi way should be explained by, and the whole point is that I don't know the details of this collective mode, but knowing that in water, it is sound that is carrying heat, and most probably in helium before it becomes quantum, somehow you should begin by this quantum classical crossover to have at least an order of magnitude explanation, because the standard quasi-particle picture is wrong by several orders of magnitude at a fraction of the Fermi temperature. These are my observations. So, of course, this is not the whole story.
For us, it's reasonable that the quantum explanation doesn't hold. I mean, we know the whole spectrum, and we see how it evolves from the quantum, the really quantum, very highly correlated fluid, to the single particle. So we have
But sorry, even you see, the only thing that I want to correct this statement is that even in a classical liquid, it's not single particles. These are collective. You see, collective modes are everywhere. You see, so if when helium-3 becomes classical, there will be a collective mode, ordinary sand, like in water. So, this is maybe the reason this problem has no, because people, we have different intellectual realms. People who work on quantum liquids were not that much aware of what happens in classical liquids.
Yeah, okay. We can discuss that further, I think. Yeah.
Yeah, well, thanks a lot, Henri. So it's yeah, very nice discussion there. So it's definitely not a closed question. So look, Andrei Golov posted a comment in the chat. So do you want to sound the comment, Andrei?
All right.
Yes,
Can you hear me?
yes.
Hi. Well, thank you very much. A very interesting talk, really. I never looked at properties of quantum fluids from this perspective. Very handful, very useful. Right. I just it comes to my memory that in late 1980s or mid 1980s, Alexander Dugaev, a Russian theorist, wrote a series of papers about sort of corresponding states of quantum fluids in the high temperature regime, where they're already non-degenerate, but still a quantum parameter can be introduced. And he showed that there is some, one can come up with some new corresponding states law. And I just put here as a reference two papers on the thermal conductivity and diffusivity, which he predicted should scale not as a t to a square root of t, but just linear to temperature. And apparently showed some tables of parameters which probably agree with that. So do you know about these papers?
Yes, you are completely right. When we published our paper, I didn't know about this paper. Afterwards, when I discussed with some of my Russian friends, Sergei Brzezinski told me that Dugaev, and I read those papers, and you are completely right. Dugaev was the only person, to my knowledge, who noticed that thermal conductivity goes through a minimum. And nobody cared about this. You see, people like Anderson, Emery wrote papers about how well, nobody asked this question, how can thermal conductivity has a minimum? Dugaev was the only person, as far as I know, who wrote explanations, who tried to come with explanation. But as you say, for reasons that I don't understand, he did not believe what Greywall was talking about, that you have a square root of t. Because a square root of t, if you don't think that much, it makes you think of gases. As I said, that you see the velocity, but actually this is not like the gas formula. And so his explanation that I have a lot of difficulty understand, as you said, predicts this kind of linear temperature dependence. Again, I don't pretend that all the problem is solved. Most probably somebody should begin with what Henri was talking about. We know very well the excitations. How can this be solved in a transport theory, Boltzmann equation with this and that? And you are right, Dugaev should have been cited. When we wrote this paper, we were not aware of many other works to be cited actually about this problem. You are right.
Thank you.
Yeah, thanks, Andrei. So any more questions? Okay, I don't see any raised hands, and everyone is muted. So yeah, thanks a lot, Kamran, for coming to our webinar. Well, it definitely was a very eye-opening talk. So as you're completely right that not many people thought about it, and yeah, putting a new perspective, this whole problem, was very very helpful. And yeah, as you said, there are many things to explore in this question.
Thank you very much for your invitation. Thank you.
Yeah. So thanks everyone for joining. So the next webinar is in 2 weeks' time, and Makoto Tsubota will be delivering this webinar. and it's not going to be the usual time because, well, it's going to be 10 UK, 10 a.m. UK time because Makoto is in Japan, and well, we can't really ask him to talk in the middle of the night. So I will advertise the next. Makoto is actually here. Yeah.
Thank you.
Yeah, so we will advertise soon Makoto's webinar, and if you have proposals for further talks, you want to propose yourself as a speaker, yeah, please go ahead, and we'll be happy to host you. So we also have on the website a section for PhD and postdoc vacancies. So if you have any, or you're looking for a job or PhD place, so have a look at that section of the site. And yeah, thanks a lot, and hoping to see you in 2 weeks.